Okay, we're recording now. All right. Any questions that you might have?
Yeah, I just have one question.
Yeah.
How's Lily doing this morning?
Eh?
How's Lily doing this morning?
Lily is doing good. She just got a treat. My wife is going to Nashville, Tennessee to pick up our daughter. So every time anybody leaves the house, she gets a nice treat. So, and after class, I'm going to the gym. She'll get a treat too. So Lily's doing good. Spoiled brat. Yeah. Anything else? So I see message in 4.3 on the homework, suppose the complex eigenvalues. What is the issue here? Even if the complex, is this problem 4.3? Answer yes or no. Yes, problem 4.3. Let me take a look at it. Four point three, use 4.2 to solve the linear system with initial conditions. Let's see what theorem 4.23. Yeah, it doesn't really matter whether the eigenvalues are real or not. I mean, you know what I mean. Okay. So you can always redo the work. So the eigenvalue can be complex. Okay. Just takes some more work, but yeah, they can be complex. Are they too difficult? If you wanna do 4.4 instead of 4.23, 4.3, that's fine. Did I assign both of them? Yes or no? All right. So if you don't want to do 4.3, do 4.4 exercise. Okay, then do if you want to if you do not want to deal with complex valued eigenvalue, then do problem exercise 4.4 instead. All right. Any questions? Okay. We're gonna continue with problems. Let's we're gonna deal with constant solution, and we're gonna look at their stability. Okay, Lily, you wanna come say hi to the class? Come, stand here. No, stand over there. Here, Lily, come. I don't know if you can see her or not. There is Lily. She's confused. Her mom just left. Yeah. Lily, you see what I have to go through. I keep the drapes drawn. All right. So basically, we're gonna look for, consider AK xn plus k plus AK minus 1 xn plus k minus 1 plus A1 xn plus 1 plus A0 xn equal to Gn. And we're gonna name this one 5.2.5. Okay? And so we have definition about that. This is stability of constant solution. I don't know what happened to my, oh, this is the one I was gonna throw away maybe. All right. Okay. All right. So let X star of n be a solution of 5.2.5. Then we say Xn is stable if for any other solution, Xn of 5.2.5 the difference between the two solutions remains bounded. That is, there is a positive constant m such that X star of n minus Xn is less or equal to m for all n bigger or equal to n naught. Okay? So B, it is asymptotically stable AS if it is stable and the limb as n goes to infinity minus Xn is equal to 0. Okay? C, unstable if it's not stable. Okay? So this is the definition. I'm going to do a couple examples. All right? So what does the theorem say that so basically what the theorem says is the following. If you have, this is x star of n, and if you have another xn, and you see the difference between them is always less or equal to m. Okay? And this is a stable. And if you have, this is xn, and this is the other one, xn, it's unstable. And we see this one is always bigger or equal to m, is becoming unbounded. And if you have this xn and this one, and then go like this is asymptotically stable. That means the difference between them, m goes to 0. That means after a while, the two graphs will be on top of each other. Okay? So that is the difference between the three. All right. Okay. Let's do an example. All right. So let's take a look at xn plus 2 minus xn plus 1 plus 1/4 xn equal to 1. And n bigger or equal to 0. So here, n0 is 0. All right. Then we can solve this to get xn equal to c1 times 1/2 to the n plus c2n 1/2 to power n. And then another one, x star of n equal 4 is another solution. Okay. Here I need a plus 4 is another solution. Actually, this is the particular solution. And so x star of n minus xn equal to 4 minus c1 1/2 to the n plus c2n 1/2 to the n plus 4 minus. And that is less or equal to, okay? So may I say, I mean, this is less or equal to C1, okay, times 1/2 to the n plus C2 n times 2 to power minus n. And that is bounded, less or equal to some number n. Okay? Because n2 to power n is less or equal to 1. Because this number here is less or equal to 1 for n bigger or equal to 0. All right? Always. And this one, so moreover, so here, x star of n equal 4 is stable. Moreover, if I look at the limb as n goes to infinity, that will be less or equal to the limb as n goes to infinity, c1 2 to the power minus n plus c2 n times 2 to the power minus n, and that is equal to 0. So actually it is asymptotically stable. Okay? You see that? Let me take a look at another example for you. Just take a look at this example first. All right, let's do another example. Xn plus 2 minus xn equal 2 and bigger or equal to 0. So we know x star of n equal n is a solution. How do you know that? Well, let's put it here. Will be n plus 2 minus n equal to 2. You see that? So that is a solution. Moreover, xn is c1 plus c2 minus 1 to power n plus n is another solution. Okay? And so equal to c1 equal to n minus c1 minus c2 minus 1 to the n minus n. And that is equal to minus c1 minus c2 minus 1 to the n less or equal to c1 plus c2. So that is n. So stable, but not asymptotically stable. Okay? Because the limit does not go to 0. All right. Okay. See if you have any questions. Okay. Now we're gonna take a look at this is section 5.3 xn plus 1 equal an xn. So this is non-constant. And an is k by k matrix. May not be constant. Not necessarily a constant. So may not be a constant matrix. If the norm of a matrix, it satisfies both cases, okay? So we may define A1 to be the max j to n, I equal 1 to n, aij. So you sum all the entry. This is called the one norm. Okay? And then B is the maximum 1 less or equal to I less or equal to n, aij, j equal 1 to n. Okay? All right? So this is called the infinity norm. So for this norm, sum the absolute values along each row and then take the biggest value. And then take the biggest value. This one, you sum all the entry in the matrix. You just sum them all. Okay? All right. So this is over the column. This is the row. And then there's another norm, which is called Euclidean norm, is the square root of I equal 1 to n, j equal 1 to n, aij squared. So what we're saying is you take the square root of each entry. Okay? All right. Any questions? So this is the norm of a matrix. All right. So let's say xn0 equal n0 and call this is 5.3.1. Okay. All right. All right. Because we're gonna talk about the stability of non-constant system. Okay, so theorem 5.3.1. Let phi n be the fundamental matrix solution of 5.3.1. Then the zero solution, and what we mean is x equals 0, of 5.3.1 is a stable if and only if there exists a positive constant n such that phi n is less or equal to n. The norm of this phi is less or equal to n. B is asymptotically stable if and only if phi n goes to 0 as n goes to infinity. Okay? So we're gonna do proof of A, but first we're gonna do this. Let phi n be the fundamental matrix solution of 5.3.1 with phi less or equal to n. Then we know the solution of 5.3.1 xn is xn equal to phi n, phi inverse of n naught, x naught. Okay? See what happened? Okay. Remember what we need to show. This is different from the constant solution. Okay, then xn is equal to phi n, phi inverse of n naught, x naught. Okay? That is less or equal to phi n, phi inverse of n naught, x naught. Okay? Now, what do we know about phi n? This is less or equal to m phi inverse O naught x naught. Now, for any epsilon positive, let delta equal to 1 over phi inverse of n naught x naught. Then we know that xn is less or equal to m, right? Phi inverse of n naught. Okay, delta is less or equal to x naught. Okay. So, no. This is not correct. This is n. Okay. Thus, for x naught less than delta, we have then that add this one to here, to this line. Add this one to this line. So less or equal to m phi inverse x naught. X naught is less than delta. You see it? That is from there. But that is equal to m phi inverse of naught. What is delta? Times 1 over phi inverse of n naught m. Okay? And here, sorry, this is epsilon times epsilon. Delta is epsilon over that. And then you can see this cancel with that, this cancel with that, and that is epsilon. So this is what we want to show. Okay? See what happened? Now for this way, we need to show now, so we need to show if xn is stable, then phi n is less or equal to n. So if xn is stable, set epsilon equal 1. That means stable means this. So that xn less or equal to phi n, phi inverse of n naught, x naught. Okay? That is less than 1 because of this one. Okay? And so phi n is less than 1 over phi inverse of n naught x naught. Okay? Which is, so I mean I can do it. So this is basically, this is n. All right. And then the proof of the other one for the stability for B, so we have xn less or equal to phi n, phi inverse of n naught x naught. that goes to 0 if and only if phi n goes to 0 as n goes to infinity. That's it. There's nothing to it. All right. Let's do an example now. Example. And that is example 5.14 in the book. So let's consider xn plus 1 equal to an xn n bigger or equal to n0, where an equal to 0, 2 plus minus 1 to the n over 2, 2 plus minus 1 to the n over 2, and 0, 0. Okay? So I'm going to take, let phi n be 2 minus n minus 1 will be square root of 3 to the n plus minus square root of 3 to the n square root of 3 to the n plus 1 n plus 1 square root of 3 n plus 1 of n plus 1 square root of 3 to the n plus minus square root of 3 to the n. Then phi n plus 1 equal an phi n. And determinant of phi n at any n is different from 0. For example, you can do it at phi 0 if you like. Is different from 0. This shows that phi n is a fundamental matrix solution. Now I gave it to you, and you can try to fill in. Okay, you can verify this and that. Okay, and you can show that. So now, what is and I'm gonna do Okay. And then phi n is less or equal to the square root of 3 plus 6. Okay. Where we have summed all the absolute value of all the entries of the entries of the matrix. Okay. So this is what we have. And so hence, by the previous theorem, let's see what the theorem is. 5.31 the zero solution x equals 0 is stable. Okay. And here it's not stable because phi n does not go to 0. 3n plus 1. Okay. Oh, any questions? All right, let's move on. No, actually, this one is n. Sorry. No, minus n. Sorry about that. 2 minus n. Okay. So that is correct. All right. Well, what you need to do here is that, for example, if you look at this entry, you'll get a square root of 3 divided by 2 to power n. Okay. A plus minus square root of 3 divided by 2 times n. Okay. And you will see this is less or equal to 1. Okay, why? Because this is less or equal to 1 and this is less or equal to 1 in absolute value. Square root of 3 divided by 2, I mean, this is less or equal to 1, so square root of 3 divided by 2 in absolute value to the n is less or equal to 1. Okay, all the time. So this is where these numbers are coming from. Square root of 3 plus 6, okay? You just add them all up. All right. Any questions? So this is less or equal to 1, and you get how many of them? And then you will get less or equal to square root of 3 plus 6. The square root of 3 is coming from here. You see 2 minus n minus 1 times the square root of 3n plus 1. Let's take one term. So this is 1/2 times the square root of 3 divided by 2 to power n times the square root of 3. You see that? That is less or equal to square root of 3 divided by 2. And how many of them do you have? You have these here, okay? And so you can play around with them. All right. Okay, so we see without looking at, because we're gonna see later on, if the matrix A is constant, then it's really easy to deal with it. All right. That's all I'm gonna do with this section. All right. So I'm gonna move on to section 5.4. I'm not doing section 5.3, all of it. I am not. Okay. So we're gonna look about xn plus 1 equal axn. Okay. And with xn0 equal x0, or n bigger or equal to n0, and that is 5.4.1. Okay. And so here, unlike the previous section, A is a k by k constant matrix. Okay. So that is actually a constant matrix. All right. So we're gonna definition the spectrum of A is sigma A, and that is the set of all lambda where determinant of A minus lambda I equals 0. So basically, this is the set of all eigenvalues of A. Nothing fancy about it. Okay. And then we're gonna denote by sigma of A less or C means the magnitude of all the eigenvalues of A are less or equal to C that is positive. Okay? So basically, if sigma of A equal 1 plus minus 2i minus 1, 0, 1, then I claim that C is the square root of 1, C is the square root of 5. Why? Because we have the magnitude of 1 plus 2i is the square root of 1 squared plus a plus 2 minus 2 squared, that is square root of 5. The magnitude of minus 1 is 1, magnitude of 0 is 0, magnitude of 1 is 1. So what is the biggest one of them? Is psi. So it is 5, this one, okay? All right, let's have a break for 5 minutes. I'll come back. All right. You see, what are we gonna do here is the following. So remember this, the spectrum, but A so for xn plus 1 equal an xn, we characterized the stability using the fundamental matrix solution phi n. Now, here, when A is constant matrix, the same can be done, but only we look at the magnitude of the eigenvalues of A. Okay? So for this one, for here, where A is not constant matrix, we cannot characterize the stability based on the eigenvalue. But if we know the fundamental matrix, then we can say something about the stability of the zero solution. However, if an now is constant matrix, then the stability can be characterized using the magnitude of the eigenvalues. I need you to understand the difference between the two. Okay? They're very important. So this one is a particular case of this. Okay? All right. So there is a theorem. Okay? If all the eigenvalues of A have M of sigma of A is less than 1, and the eigenvalues are distinct, then the zero solution of 5.4.1 is uniformly asymptotically stable. I did not talk about this, but which implies asymptotically stable. So all I care is about asymptotic stability. If I am teaching this course to all math students, then I will be happy to talk about uniform asymptotic stability. But it's a little bit difficult and I don't have the time to dwell on it now. Okay? So this is a theorem, and the proof of it is in the book. I'm not gonna go through it. Okay? All right. Here is another theorem theorem 5.43. Let lambda 1, lambda k be the eigenvalues of A. They may not be distinct. They may not be distinct. Width of sigma of A is less than 1, then all solution of 5.41 are bounded and its zero solution is asymptotically stable. Okay? Again, I'm waving my hand here. Okay? Let me see. I may have an interesting theorem. So the stability depends on the eigenvalue of A when the matrix A is constant. Okay? Now there is another theorem I would like to list. Okay? For this is theorem 5.4.2. Suppose sigma of A is less or equal to 1. Notice now they can be 1. Where the eigenvalues with and sigma A equal 1 are simple. So simple mean they don't have multiplicity. That means multiplicity 1. Then all solutions of 5.4.1 are bounded and its zero solution is uniformly stable. So these are important things. For example, if I have lambda 1 equal 1, lambda 2 equal to 1 over the square root of 2 plus or minus I times 1 over the square root of 2, and lambda 3 equal to 1. Is this allowed or not? Notice sigma of A is equal 1, because this one here will be 1. Okay? But is this allowed? Tell me. What do you think? Hello? Anybody? Well, it is not allowed. This is not allowed since 1 is of multiplicity 2. You see? It repeats, so it cannot repeat. Let's say we write the solution. X1, xn equals C1 times 1 to the n plus C2n times 1 to the n plus this one here. What would be? Will be rho is the square root of 1 over the square root of 2 squared. That is 1. So that will be 1 to the n C1 cosine n pi over 4 plus C2 sine n pi over 4. Well, you see, so that is C1 plus NC2 plus C1 cosine n pi over 4 plus C2 sine n pi over 4. Because of that is unbounded. That means xn goes to infinity as n goes to infinity. But the theorem told us all solutions of 1.4 are bounded. Well, they're not. But this does not contradict the theorem because the first eigenvalue is repeated. Okay? All right? Any questions? What if I have lambda 1, lambda 2 equal 1/2, lambda 3 equal 1/2, and lambda 4 is 1 over the square root of 3 plus or minus I times 1 over the square root of 3. Is this allowed? Take a look at the statement of the theorem. Is this allowed? Is everybody with me? Is anybody with me today? Actually, it is allowed. It is allowed. Why? Where the eigenvalues with m of sigma equal 1 are simple. Which one are 1? This one. And it does not repeat. So this is good. You see this repeat, but Those has magnitude less than 1. So this is fine. And this is fine. So the answer is yes. This is allowed. Okay? You see what happened here? All right. Now I want to say something. Okay. Another thing is so theorems 5.4.1 through 5.4.3 do not hold if the matrix A is not constant. Warning, okay? Okay. I want to do something here. If I take an equals 0, 2 minus 1 to the n over 2, 2 plus minus 1 to the n over 2, and 0. Then this has eigenvalues of lambda equal to lambda equal to plus or minus square root of 3 divided by 2. So the lambda or the square root of 3 divided by 2, that is less than 1. Right? However, solutions of xn plus 1 equal an xn are unbounded. And this is exercise 5.16. Okay? That's exercise 5.16. All right. How much time do we have? Okay. This is 5.51. Grunwald's inequality. Okay. Let n0 bigger or equal to 0 and consider n of n0. Okay. Let un, alpha n, beta n, and gamma n be non-negative scalar sequences for all n bigger or equal to n naught. Assume un less or equal to alpha n plus beta n s equal n naught to n minus 1 gamma s us. Then we have un less or equal to alpha n plus beta n s equal n naught to n minus 1 alpha s gamma s times r equal s plus 1 to n minus 1 1 plus beta r gamma r. There we go. That's called the Grunwald inequality. Okay. And you see there is no more un here. Like here, all of a sudden it comes out. A proof. Let phi n equal to s equal n naught to n minus 1 gamma s us. Then del phi n is s equal n naught to n gamma s us minus s equal n naught to n minus 1 gamma s us, and that is evaluated at n gamma n un plus s equal n naught to n minus 1 gamma s us minus s equal n naught to n minus 1 gamma s us. These cancels, so this is gamma n un. Okay, but what does that mean? Okay, so from here or del phi n is less or equal to gamma n times un times alpha n plus beta n S equal N naught to N minus 1 gamma S US. Okay? And that is gamma N, alpha N, plus beta N, phi N, because this one is phi N. Okay? You see what happened? Now, let's work out backward. So, we have phi n plus 1 minus phi n equal to less or equal to gamma n alpha n plus gamma n beta n alpha n. Phi n. Okay? So phi n plus 1 minus 1 plus beta n gamma n phi n. So I brought this over here, less or equal to alpha n gamma n. Okay? Now, we know 1 plus beta n gamma n is positive because beta is bigger or equal to 0, gamma is bigger or equal to 0. Hence, this is I call 5.5.3. 5.53 is equivalent to delta of S equal N naught to N minus 1, 1 plus beta S gamma S minus 1, phi S, okay, is less or equal to here alpha n gamma n S. We've done something like this before. 1 plus beta S gamma S minus 1. Okay? And what do we know about this? You see, this is gonna be, this is the product. So if I sum from, so we're gonna sum from n0 to n minus 1. So we're gonna get phi S equal n0 to r minus 1, 1 plus beta S gamma S minus 1, phi S from r equal n0 to n. Okay? And that is S equal n0 to n minus 1. I'm gonna flip alpha S gamma S, the product R equal N0 to S. No, to N. To N. 1 plus beta R gamma R. 1 plus beta R gamma R to minus 1. Okay? Okay, but this one is S equal N0 to N minus 1, 1 plus beta of S, gamma S of minus 1 phi N minus okay. All right, so phi N0, where is phi N, by the way? Remember, what did we do? You see phi N0 here is 0. Put N0 here. Phi N, N0 will be S summing from N0 to N0 minus 1, that will be 0. So minus phi N0, that is 0, equal to all that. And then you will obtain phi N less or equal to S equal N naught to N minus 1, alpha S, gamma S, or equal S plus 1 to N minus 1, 1 plus beta R, gamma R. Okay? But what is phi N? Remember, phi N, I erased it. Remember what phi N was. Phi N was S equal N0 to N minus 1, gamma S US is less or equal to all that. Okay? Okay, hence UN less or equal to alpha N plus beta N S equal N0 to N minus 1 gamma S US. This is by definition. You see, we know this. But now, what is gamma SUS? Gamma SUS is less or equal to all that. Okay? Which is less or equal to alpha N plus beta N. And what is gamma RUS? So that would be S equal N0 to N minus 1, alpha S, gamma S, a pi, all that here. You see it? And that give us this one. Look at it. Alpha N plus beta N times all that. And that is this one here. And you will get it. So next time, I will do special case with it. And why am I doing ground walls inequality? Because I need it for perturbed system. I want to look at perturbed system and see how the original system is affected by the perturbation when it comes to stability and other qualitative analysis of the solution. So ground walls inequality is very, very important, a little bit complicated, but it is of a lot of use when it comes to dealing with perturbation or perturbed system. I'm gonna stop here and I will see you tomorrow. I'm gonna stop recording.
Hey, Professor.